All right, Math 1 people, this is lesson 6.2, radicals and rational exponents. In Khan Academy, we're working in exponents and radicals, and after this lesson, you should be able to complete skills 4, 5, and 6. Your objectives are that you'll be able to use square root and cube roots to solve rational exponents, and you'll also be able to solve unit fraction exponents. So before we dive into the lesson, what do these words mean? What's a radical in math? When you see that word in a math class, you should think of this symbol. You might think of that right now as a square root symbol, but it's really just a radical symbol because we can have different numbers inside the crack. If it's a square root, we often just don't write a number at all, but that would be the same thing as putting a 2 in the index. This is technically also a square root, but I can also change the index to a 3. That could be a cubed root, or you could have a fourth root, and so on. Either way, these are radical expressions if they have this symbol here. Now, rational, when you see that word in math, you should think of fractions. So suppose I have two integers, m and n, where m and n are both integers. M over n is a rational number. It could be a decimal, it could be a fraction, but that's a rational number. So if we're talking about rational exponents, that means we're going to see exponents that are fractions today. In the last lesson, you saw exponents and properties of exponents, but they were all integers. Today, you'll see some fractions in the exponent. Okay, so the first blank here is a square root. You've seen square roots before. It's the number that, when multiplied by itself, gives us the number inside the radical. So if I ask you, what's the square root of 1? Well, 1 times itself gives me 1. So the square root of 1 is 1. What's the square root of 4? Well, 4 is 2 times 2, right? So the square root of 4 is 2. The number multiplied by itself to give you 4 would be 2. Similarly, the square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. And I'm hoping you see the pattern. I'm asking you to square root the first 12 perfect square numbers. We'll have 6 and 7, 8, 9, 10, 11, and 12. So in this chapter, you are going to need to know your perfect squares. If you don't have them down already, you might want to write this on a note card, but that's going to be up to you. If you already know that 144 is 12 times 12, you probably don't need to add this to your note card. But I suspect that fewer of you have your perfect cubes memorized, and you're going to need those too for this unit. So the cubed root of a number is a value that when multiplied by itself 3 times gives us the number inside the radical. So again, when you see the cubed root of 1, well, since 1 times 1 times 1 gives us 1, 1 is the cubed root of 1. And since 2 to the third power, 2 times 2 is 4, times 2 is 8. That means the cubed root of 8 is 2. The cubed root of 27 is 3, because 3 to the third power is 27. We know that the cubed root of 64 is 4. The cubed root of 125 is 5. You can check. 5 times 5 times 5 is going to give you 125. And again, hopefully you see the pattern. I'm asking you to cube root the first 12 perfect cubes. All right, so that's mostly just for your reference. But now that you are thinking about perfect square numbers, perfect cube numbers, let's take a look at example 1. And I'm asking you what number times itself, because this is a square root. There's no 2 written, so we know the index is just 2. What number times itself gives you 16/9? You may or may not be able to pick this one out yet, but I suspect that some of you might think it's 4/3. And if you thought that, you're right. The thing is, it would be nice, I'm going to put a question mark for now because we haven't really proved this or talked about it, but wouldn't it be nice if we could just square root the 16 and then square root the 9? Because 16 is a perfect square. The square root of 16 is 4. And 9 is also a perfect square, and the square root of 9 is how we got that 3. I'm going to spoil it for you. This is true, but you need to know why. So before we go on to any more examples, let me show you why we can split that square root so that we can just square root the numerator and denominator separately. The reason we can do that is because every radical expression can be written as an exponential expression. In other words, all those rules you saw in 6.1 about properties of exponents also apply to radical expressions because radical expressions are exponents, right? So we already talked about this. The index is the number inside the crack. The radicand is what you call the number inside the radical symbol. And then this equation here is the key takeaway for lesson 6.2, but we're going to build upon it. We're going to make a version of this yellow highlighted rule that I think is more general and more applicable. So bear with me just for a moment. Suppose I have that same nth root of something, right? So I'll use the same colors I did before. N is going to be our index. And I'm going to change our radicand so it's not just a number, a. Let's say it's a to a power that's an integer. So m and n are both integer values. But let's say I want to find what's the nth root of a to the power of m. I can still use this rule to rewrite the expression as my radicand, the stuff inside the radical, but it's going to be all to the power of 1 over n. But wait a minute. Now I have an exponent or something raised to a power and all of that raised to another power. And that was the power to a power rule that you saw in our last lesson. If you're not sure what I'm talking about, go back and watch 6.1 again or go back and look at your notes. This is equal to a to the power of m times 1 over n. And we can multiply that. M times 1 over n, that's a to the m over n, right? Because m over n, there we go. Because this is m over 1 and we can multiply straight across, right? Let's say, if I stopped here, I could have also said that a to the power of m times 1 over n, doesn't multiplication have the the commutative property, right? So in other words, order does not matter. I could switch these two, switch m with 1 over n, and it would still be the same thing. Or I could write it as 1 over n times m. And if that's the case, I could work backwards and say that's a to the 1/nth all to the m power, which is the nth root of a, and then raised to the power of m. Do you notice the subtle difference here? We started with m as an exponent inside the radical. The m was part of the radicand. But now m is not. I was able to pull m out. So let's sum this up. I know there's a lot going on. Bear with me. Our more general version would be that the nth root of a to the power of m, that's the same thing as a to the m over n, which is the same thing as the nth root of a all to the power of m. You can use any time you see one of these versions, you can replace it with the other. This is a very powerful equation that you should include on a note card and definitely know this for our chapter. Okay. So, in short, since radicals are exponents, we can use all of our exponent properties, and one of those properties was the quotient rule from last chapter. So we are totally allowed to make this jump. I'm going to erase the question mark, and that's how we got our 4/3. All right, let's try example number 2. What number times itself gives us 0.64? You could put a 0 there if you want. And you could go different ways. I like to think of fractions, but you could also see that, hey, 64 is a perfect square. It's 8 times 8. But now I've got a decimal there, and maybe you just guess and check. And maybe try 0.8, and if you try that, 0.8 times itself is 0.64. So the square root of 0.64 is 0.8. Another strategy, just so you have a different tool to use, is that you can always write this decimal as a fraction. 0.64, remember 6 is in the 10th place and 4 is in the 100th place. So this is the same as the square root of 64 hundredths. There's 2 digits after the decimal, and there's 2 zeros to make 100, right? And then you can do just like we did in example 1, square root 64, then square root 100. You would still get 8/10, which is 0.8. You could even reduce it to 4/5 if you prefer fractions. All right. In example 3, again, there's multiple ways to do this. If you saw that 216 and 27 are both perfect cubes, that is fine. You can cube root the numerator and get 6, cube root the denominator and get 3, and then reduce your fraction to get 2. You could have also noticed that this fraction reduces. 216 divided by 27 is actually 8. So if you reduce that fraction first, that's okay. The cubed root of 8, what number times itself gives us 8? Well, it's still 2. So either way, you get 2. And our last problem, please note there was a typo. So can you move that decimal 1 to the left and move the decimal in practice problem 4 1 to the left as well? All right, now that you fix your typo, we're trying to find the cubed root of 0.125. Again, maybe you notice that 125 is a perfect cube, and you just guess and check, and you get that 0.5 is the answer. That's fine. 0.5 is the answer. But if you turn it to fractions, you might have noticed that I'm asking you for the cubed root of 125 over, there's 3 digits after the decimal point, so if I convert it to a fraction, it would be a 1 with 3 zeros in the denominator, and 1,000. And the numerator and denominator are both perfect cubes. We'd end up with 5 over 10, which reduces to a half, and that's the same as 0.5. All right, try practice problems 1 through 4 on your own, and then come back and check your work. All right, so for practice problem 1, you should have got 10/9. For practice problem 2, I'm asking you to square root 1.21. You could have written it as a decimal or as a fraction. Either way, it's 1.1 or 11/10. The cubed root of 64 over 512 is 1/2. And the cubed root of 0.216 is 0.6, or as a fraction, it would be 3/5. Okay, so we've got our rule here. The next practice problems are just an exercise in jumping from radical form to rational exponent form. So if you see a base to a power and an exponent, you need to know that that power is the numerator of the exponent and the index is the denominator. So this becomes 5 to the 2/3 power. Remember, square roots mean the index is 2, so there's a little invisible 2 in the crack. So the square root of 3 to the 5th power would be 3 to the 5/2 power. And then same thing here, 4 to the negative 2 power, that's 4 to the negative 2 over 3, because we have a 3 in our index. All right. So try practice problems 5 through 10, and then come back and check your work. Okay, so this expression can be written as 3 to the 2/3 power. Our index, or our exponent stays where it is, and then our index becomes the denominator of the exponent. Same thing for practice problem 6. We end up with 6 to the 3/8 power. Practice problem 7 can be written as 5 to the 9/4 power. Practice problem 8, 6 to the power of 2/3, could be written as the cube root of 6 squared, or the cube root of 6 all squared. Practice problem 9, I gave you 2 versions again. You don't have to write both, you can just write one if you'd like. And then same thing with practice problem 10, d to the 3/7 power could be written either of these 2 ways. And we're almost done. I just have one quick example. And I'm hoping this example shows you why I'm giving you 2 different ways. Why did I write these 2 different versions? Let's say you need to find what 343 to the 2/3 power is. According to our notes, you could write it one of 2 ways. You could totally write it as the cubed root, because again, the 3 in the denominator is what goes in the crack. That's our index. It could be the cubed root of 343 squared. So we have to find the cubed root of all of this stuff. But if we do it that way, and let's say for whatever reason we're not using a calculator, we're just trying this out, that means we would have to find out what 343 times 343 is. And that's a big number. That's kind of a pain to deal with. It takes more time, but we could do it. It would be 117,649. And then we would be asking ourselves, what number to the power of 3 gives us 117,649? Again, it can be done, but do you really want to do all this? Especially if it's a question where you're not allowed a calculator. It would be 49 though. If you write it the other way, if you're able to recognize that, well, I eventually need to raise 343 to the power of 2, and I need to cube root, and if you understand properties of exponents and you know you can do this in either order, this becomes a very quick mental math problem that you don't need a calculator for, because then you can write it as the cubed root of 343 squared. And I can cube root 343 without a calculator because I know my cubes. Remember those cube numbers we wrote on our first page? We know that the cubed root of 343 is 7. And we know what 7 times 7 is. It's 49. So hopefully that helps explain why you should be comfortable writing it in either way. But as always, ask a question at the end of the video, and I'll see you all in the next one.